Ladies and gentlemen, we have a very special guest on the program today, Antonio Zamora, and an unlikely character. He is famous for his book, which is The Neglected Carolina Bays, and he's done some research on the Carolina Bays. There it is. Now, Antonio is not a geologist. It's quite interesting. He started in the field of computer programming and chemical information science. He ended up working for, I think you just said IBM. In the end. And I think he was working on algorithms or something like that. But then about a decade ago, you suddenly had an interest in geology, and it's fascinating the work you've done. You are, I believe, one of the leading scientists in the field at unraveling what these impact structures may be. And it's a pleasure having you on the program.
Thank you.
So now you didn't come up with the impact hypothesis and the ice projectile hypothesis. This all came to light in 2006, you just revealed to me, with the Firestone book.
Yes, like I mentioned, Firestone wrote a book in 2006 along with Alan West and Simon Warwick Smith. And in this book, they have a chapter called The Carolina Bay Craters. So they mention these structures don't exist anywhere in the world except here, and so the mechanisms that created them must be unique.
Well, they do try to say that there is similar bays in Australia, these salt lakes. Are you familiar with that?
Oh, yes.
And they don't look anything alike.
No, they are not elliptical. They don't have raised rims. We will go through some of these characteristics. Maybe we can start with the aerial image that you introduced in one of your topics before.
Before we get started, guys, if you're out there, Antonio Zamora has a YouTube channel. You can come over and subscribe. You can follow all of his work from beginning to end, and he takes you through step by step. And in fact, he's even now dissecting individual bays. So if you're interested in this topic, there is a worth of knowledge over there. Do you want to comment on your channel?
Oh, well, I started it as a repository of information. When I wrote my second book on the Carolina Bays, I called Solving the Mystery of the Carolina Bays. Well, it's a thin book, okay? Compared to my new book, which is a lot thicker.
Yeah.
And when I put the videos out, some people commented, and they had some good questions and good comments. And so I used that opportunity to create new experiments to demonstrate how the hypothesis, the glacier ice impact hypothesis, and the impacts on consolidated ground would work. And so this gave me a lot of extra material for my current book. Go to A010, okay? This is...
Does this one work, the 1930s?
Yeah, this is the one, yes. Okay. This is what was the first image produced by an aerial survey for the Ocean Forest Company, taken in 1930. And this initiated a lot of conversation about the Carolina Bays. Why were they like elliptical or ellipses, and why were they oriented all in the same way? And in 1933, Frank Melton and William Shriver from Oklahoma State University wrote a paper called The Carolina Bays. Are they meteorite scars? You know, that was the question that they asked. And they did some research, and then additional scientists went and looked inside to look for meteorite fragments. They did not find anything that looked like extraterrestrial. And so in 1942, Douglas Johnson, a professor at Columbia, wrote another book, The Origin of the Carolina Bays, where he proposed that they originated from artesian springs, and then they were which made like little lakes, and then wind and water action created the raised rims. And the idea of the artesian springs has basically died off. Nobody, it has been basically been disproved. But the wind and water hypothesis has many supporters even today.
Yeah, I couldn't believe that when I did research on the topic. First of all, being a geologist, the initial explanation is ludicrous simply because of the symmetry of all the bays. You would need to have exactly identical springs and wind patterns. It just doesn't hold weight at all. It's ludicrous. And the fact that 60, 70 years later, the majority of geologists that give it a cursory view agree with the ludicrous wind and water idea.
Well, okay. If we go to the next slide, the A014, that one. See, this is a typical Carolina Bay using modern LiDAR imaging. The image is, the LiDAR images are created by Michael Davies. He has a database of images. And the colors basically indicate the elevation, the topology, and or topography. Then you will notice they are elliptical, they have raised rims, and they are oriented all in the same way. And
well, it also appears as if the southeast rim is the most prominent.
That is correct. That is correct. And so the initial reviewers or the people who studied the Carolina Bay said, well, this means that there were impacts from the northwest or the southeast, okay? And so this is why there's extra material on that side. And that turned out to be correct. I will explain why when we get to the experiments. But notice that these Carolina Bays overlap right on top of this big one. Yes, there is that small one, which was overlaid by the big one. So that means that the impacts happened over a period of time, actually minutes, okay, where one impact came on top of another. And so some of these large rims may be because one impact happened just on top of another.
Yeah, in fact, what I would posit here, looking at it and using the law of superposition and logical thinking, is that what I envisioned was that this pockmarking, so if you have a whole field of projectiles in the form of ice, it is going to just continuously recycle the surface for a period of time in those minutes, where you'll literally get hundreds of thousands of impactors on top of one another and one another. And this one we're looking at was the last one at the very end and made the best impression.
Exactly.
Yeah.
And so, okay, we can then go to the next slide, which shows that, no, the one about the Nebraska rainwater basins, the one you had, right, that one, see. These are perfect ellipses separated by 1,800 kilometers. You have the ones in Nebraska, which are pointing toward the Great Lakes, and you have the ones in the East Coast, which are pointing toward the Great Lakes. See, in 2001, William Sanner and Mark Kusila pointed out the similarities between the Nebraska rainwater basins and the Carolina Bays. However, they proposed that the Nebraska rainwater basins originated as blowouts. Again, the wind hypothesis, okay? And but one thing became very clear, that they were not extraterrestrial, and there was now a possible point of convergence. And so we would take a look at the next slide. It's A24, no, the previous one, A24.
The one we just had?
No, A20, this one here. See, in 2009, Richard Firestone published this image, and he showed like the Nebraska rainwater basins and the Carolina Bays, and then he showed some in Texas and some in Kansas, and some in South Carolina, showing a radial distribution. So by 2009, it was known that the origin was not from outer space, but that it had come from someplace by the Great Lakes. But Firestone also said, hey, look at Hudson Bay, which is very circular. And a lot of people have said, well, this is where an impact happened. Well, a lot of research has shown that Hudson Bay is not the result of an impact, at least not anything that can be measured recently. And but the idea of convergence is already shown in this slide. So if you go now to the next slide, it shows this is a more refined study by Michael Davies showing the convergence point of the Carolina Bays. And what Michael Davies did is he what Michael Davies did, he established a database of Carolina Bays with
so what he used arcs. Before Firestone was just using straight lines, and this guy incorporated the projectile arc motion.
Yes, these are the trajectories, ballistic trajectories, basically, great circle trajectories, and he adjusted for the rotation of the Earth, and he figured out that the intersection was at Saginaw Bay. Now,
people out there listening have to realize that at this time, 12,900 years ago at Saginaw Bay, there would have been approximately 2 kilometers or more of ice.
Yes, that is true. However, I have been challenged on that, okay? And in that they say, well, this ice came and receded and expanded. And so at 12,900, which is the younger dryad boundary, there was no ice in Saginaw Bay. However, if you take a look at a lot of the lines, and you do this work yourself, you find out that a lot of the intersections are like in Lake Michigan, not necessarily Saginaw Bay. And so even if this location is not correct, there was a substantial amount of ice by the Great Lakes region. And so right now, the only way that we have is to infer it from the moraines where, the ice glaciers went and dropped some stones. And so they say, well, there was ice up to here at this time. And so then trying to date when that date runs into various problems, including the carbon dating, which is affected by the amount of carbon-14 in the atmosphere during the time. And, if there are fires or whatever, they change that. And so it is very tricky to get an accurate carbon-14 dating or radiocarbon dating for when there was ice in the Great Lakes region. And we go to the next slide, which is the B010. One before. No, it's B010, Firestone's Younger Dryas Hypothesis, publication by.
Okay.
The one before. There we go.
All right. Yeah, so now comes in the microspherules and the other cosmic stuff.
Yes. You have mentioned this before, and this is the 2007 paper that actually created the big arguments. When the book was published, this Cosmic Catastrophes book was published, nobody paid attention. It's not a peer-reviewed publication. But this peer-reviewed publication with 26 authors, hey, that is the foundation of science. And if it's wrong, there will be a lot of criticism. And this is exactly what happened. Uh,
Yeah, they got tore up. They people didn't like what they had to say.
Yes. And so one of the major signatures of this catastrophic event was this microspherules that were supposedly in that layer of 12,900 years ago. And if you look at the next slide, which is the one with the that one, this one, this shows the Younger Dryas field. This was in a publication by James Whitkey as the primary author, and Firestone was one of 27 co-authors. And they always use the Australasian field of the tektites to compare the size of how far away some of these extraterrestrial impacts can eject material. But this Australasian tektite strewn field has been dated to 788,000 years ago. So it has nothing to do with the Younger Dryas, okay? It's just size comparison. And the citation here in this slide is for a 2000 and what is it? It's what is it? 2019 paper, which found some Younger Dryas material at the Younger Dryas boundary in Chile. So now we can say that some of that, some of the ejecta from the Younger Dryas went as far as South America. And there's also some other work that has been found in Africa. So it's really...
So in Pilauco, the Chilean site that's the outlier to the south.
That's right.
What did they find there on the Younger Dryas boundary? Are they finding microspherules, or
they're finding all the markers of the Cataclysm, the microspherules, and some of these other markers of the impact. Okay?
Which would be a platinum spike potentially.
Well, the platinum spike is something that has been found far and wide. If you take a look at the next slide, which is the B040, is the platinum spike. This one. See, I read a commentary by Jacobson, who is one of the co-authors of the paper that produced this, and they say what we wanted to do was kill the Younger Dryas impact hypothesis once and for all. And so as an effort to debunk the Younger Dryas impact hypothesis, they went to the Greenland ice sheet and looked for any evidence of any extraterrestrial materials at the 12,900 year boundary. And lo and behold, they found platinum. Like in the case of the impact with the dinosaurs, they found iridium as the major impact marker. For the Younger Dryas, it's a platinum anomaly, a high concentration of platinum.
There is also simultaneously on this spike a beryllium-10 spike that lasts for a similar length of time. So that's very interesting.
Yes, I saw that in one of your slides, and I thought that's also very interesting. Yes. It implies some kind of radiation or something like that. And so
well, also to be clear, a platinum spike in geology can also be showing large volcanic events.
Yes, but in this case, those were eliminated. As a matter of fact, when this paper was published by Petayev, uh, Mark Boslow, who is a great antagonist of the Younger Dryas impact hypothesis, said, hey, you're confusing that. That could have been from an earlier impact or from volcanic and so forth. But these authors were very conscientious, and they eliminated all the possibility. And so they said that this was from an iridium poor and platinum rich meteorite that was, they say, like an iron meteorite that would have actually impacted the Earth, would not have resulted in an airburst. So whereas the Younger Dryas impact hypothesis from 2007 said there was an airburst, now the scientists are saying no airburst, this is an impact, okay, which is good for me, in that I require an impact on the ice sheet in order to get ice ejected for the making of the Carolina Bays.
Well, not necessarily, Antonio, because we know from visual inspection of the Tunguska site that there may not have been an impact. It might have discharged above the surface. And then we've witnessed the Chelyabinsk, 2 events in Russia where objects coming in discharge with the Earth and vaporize above the surface. If you get a big enough chondrite or meteorite coming in at that ice sheet, and then it explodes above it to the tune of like 100 megatons, you are going to fracture and blow out that sheet.
Not
as good as if you actually hit it, obviously.
Yes, actually, when you hit it, and we'll discuss this when we go in a couple more slides. Go to the next slide, which is the glacier ice impact hypothesis. There we go. See, basically, what I proposed was that there were 4 mechanisms, and I wanted these 4 mechanisms to be something that was well established, as like you mentioned before, well established in the geology and physics community, so that nobody could say this didn't happen. Okay, these are actual things that you can show can happen experimentally, and so the emphasis has been always on things that can be derived mathematically or experimentally. And so the idea is that a meteor impact on the Laurentide ice sheet ejected ice boulders. And then the secondary impacts by the ice boulders liquefied on consolidated ground close to the water table. And the oblique impacts of the ice boulders on the liquefied ground created inclined conical cavities. And then viscous relaxation reduced the depth of the conical cavities to produce shallow elliptical bays. And so this was basically what I published in a peer-reviewed publication, Geomorphology. And so now we can go to the next slide and show how some of these things can be tested. And the one previous from C012 from Peter Schultz. There we are. See, Peter Schultz is a professor at Brown University, and he has been experimenting with NASA's Ames vertical gun to study hypervelocity impacts on ice. And he was a co-author of the 2007 paper with Firestone. And his experiments have always shown that you take a pellet and drive it into an ice sheet, and boom, it destroys the ice sheet and ice particles fly out. And then in the next slide, the next slide shows it's the one another impact from there. No, you passed it there. See, this is another impact, and here you can see Dr. Schultz has hit an ice sheet with a pellet, and you see all these ice particles or ice boulders coming out. This is, of course, small because it's a small-scale experiment. But an impact has basically 3 stages. There's a contact and compression, where the projectile hits the target, and then it builds up immense pressure, and then you have excavation, which is basically an explosion as that energy is released. And then once all that energy is spent, then you have the modification phase where gravity takes over and things start falling back. Yes. And so with these three stages, you can see that if we have an iron meteorite like Petayev proposed, which has rich in platinum, it would go under, penetrate the ice sheet, the shock wave would fracture the ice, and then as you have this explosion, all those pieces of ice go flying out. And one of the things that I noticed was that the Carolina bays have a width to length ratio of about 0.58, which corresponds to an impact angle of 35 degrees. Now, 35 degrees is a very acute angle for an impact. And normally you can see 45 degrees, but which means that there was a lot of steam generated, and a lot of this high pressure steam will also help to propel the ice particles or the ice boulders. And this is why we had a range of 1,500 kilometers. Take a look at the next slide, the C020.
I want to just comment on this slide. It appears as if the pellet came from the right of the screen here, and then you can see the ejecta moving off to the left in clusters. It looks like they're grouping in clusters. Not only that, in the clusters, I'd say, albeit a little blurry, there is a huge range in sizes from really microscopic ice dust to very large chunks. And
That is correct.
We have that same range in Carolina Bays where some are 13 miles and others are a few hundred feet.
That is correct.
So that's an interesting observation there.
Yes. Okay. This is the one, what I call the mathematical empowerment from the laws of physics. And we can just go from the top. The Bay geometry with its width to length ratio enables us to know at what angle that Carolina Bay was made. And if we assume that that impact angle is about the same as the launch angle, then we can use ballistic equations to calculate projectile speed, height of the trajectory, and the flight time. And this is important for establishing the sequence of events during the cataclysm. And then from the size of the Carolina Bays and the projectile speed, which we know from the ballistic equations, we can calculate the energy of the impact and actually the size of the projectile. And from the size of the projectile, using the density and the equation for kinetic energy, we can then take all those things together and calculate the energy of the extraterrestrial impact, the mass of the ejecta, and the volume of the ejecta. So we will know how big an area of ice was ejected, and basically the size of the comet or asteroid that impacted the Earth. Okay, let's take a look at the next slide. It's the one, it looks very similar. No, it looks very similar to the one that CO40.
I don't have them numbered.
See, okay, this is good. This is the computing projectile size from crater diameter. This is a program coded by Professor Jay Melosh and Ross Baer. And given the size of the Carolina Bay and the speed at which the projectile is coming down, we can calculate the size of the projectile and the energy. And so in this particular case, this is a Carolina Bay of about 900 meters in length. The projectile size would be 180 meters in diameter, which would be about the size of Yankee Stadium, which is illustrated inside the bay. So with bleachers and all, that's Yankee Stadium right there. And the energy...
That Yankee Stadium is the size of the ice chunk that made that bay.
Exactly. In order to make a bay that big, you need a chunk of ice that big. It works out that normally, if you take the length of a bay, the projectile has a diameter of 1/5 of the length of that bay. And in this particular case, that impact would be equivalent to 3.03 megatons of TNT. Now, this is megatons. Now, the bomb in Hiroshima was only like 20 kilotons. So this is a lot bigger. And there's a formula for converting the energy to magnitude, earthquake magnitude. And so here on the right side, I calculate that this 3.03 megaton impact, which is 1.27 times to the 16th joules, corresponds to a magnitude 7.8 earthquake. And
that's mind-blowing, because this is just one bay, and some have calculated there could be 500,000, and that's just the final impactors, if you were listening at the beginning. So right. This is a catastrophic seismic event happening right after the catastrophe. That 500,000 number was given by Prouty in 1952 in one of his papers. But see, this was before LiDAR, so he didn't have the clear images that we have today. Yeah. I think it could be in the millions rather than 500,000. That's mind-blowing.
Yes. Now, I would like to show you a slide C40, which is using the least squares method, this one. And I have made available on GitHub the Python programs for fitting ellipses to Carolina bays. And you can go with Google Earth and just make little markers around the perimeter of the Carolina Bay and use latitude and longitude, or you can use a digitizing program like a WebPlot digitizer, which I used for this slide, and then just go around putting the points, and then you send those points to the Python program, and the Python program will fit an ellipse to those points. And you can see that, hey, these are definitely elliptical by the least squares method. There's no question. It's not oval. It's not, And if you go to C060, slide C060, which basically is the cover of my, it's the cover of my book, C060.
I don't have them numbered, Antonio.
Well, look for one that looks like this.
Oh, okay.
There we go.
Boom.
See, now that little rectangle that you see in the middle is actually a farm, a big farm with 8 buildings. But see, you can see that this elliptical geometry is not just a coincidence, it's an attribute of the Carolina Bays. Well-preserved Carolina Bays have elliptical shape. And you can see some are inside of others. There are many examples here of bays inside others. So it was raining ice boulders, which were creating penetration funnels, which were then being, with the vibrations, were being reduced to flat terrain through viscous relaxation.
Which is the term in geology is liquefaction. And,
Yes, well,
unique, and this area is unconsolidated sediments in the coastal plain region. So there is plenty of this going around to liquefy.
This is why I have the picture of the truck sinking.
Yeah.
Yeah. And if you can get it up there. There we go. So this is liquefaction. You know, you're driving on a sandy road, and all of a sudden there is an earthquake of magnitude 6.3, and all of a sudden you're facing the center of the earth. And so this is, can you imagine during this bombardment, you're going to have the ground under you turn into a quagmire, a quicksand. You cannot run, you're trapped. And then a nice boulder comes and hits you.
Yeah, and so here we're looking at liquefaction during a 6.3 earthquake.
That's right.
Probably very loose sediment, but we're talking there isn't even probably an earthquake happening less than magnitude 7 in all of the Carolina Bays. So they're estimated to be between 7 and low 8 magnitude. And if you have millions of these earthquakes happening simultaneous, it's almost unimaginable the type of liquefaction, which gives credence to the perfect flatness of these impacts.
Right. And we can take a look at the black and white image with the Carolina Bays all over. There. No, the modern one.
Oh, okay. That's got to be the other direction.
Oh, okay.
No, I can't. I don't. There it is.
There we go. No, but that. Go back. There we go. See, this is the result of saturation bombardment. Okay, you know, when I tell you this is, you may have driven over here at some time. This is 25 kilometers southwest of Fayetteville, North Carolina. And see that little twisted line that you see on the right hand of the screen, that's I-95. That's I-95. And the straight line is a railroad line. So, you know, we're driving through all these Carolina Bays all the time. But when you look at them in the satellite image, you only see plowed fields. You don't see the Carolina Bays. LiDAR brings them out because it has, like in this image, like a 20-time exaggeration. And so you're able to see the shape of the surface very clearly. And take a look at the bottom of the slide. It has the a scale. There you go. Notice that is what, 4 kilometers?
5
kilometers. Yeah. And so you have this large Carolina Bay right next to it, you know, which is like 4 kilometers.
Yeah, right.
And I figured out that this was like an ice boulder like 800 meters across or something like that would have made that. Wow, that's a big one. And notice some of them have undefined edges, like the one that you just pointed at with this drainage ditch on it. Some of these impacts were on places that had water, and so they created splashes.
Yeah, you got to remember, this was supposed to be, this area has very high groundwater. So it's a very saturated region to begin with. And a lot of it is still swampy today. And,
Yes.
and for good reason, because it might still be remnant moisture from the ice bolt projectiles that actually changed the environment. It stayed that way.
Well,
Because what we do know is that there are very unique ponds and lakes that have formed in these Carolina bays, and they have very unique biology in them. They're almost like microcosms.
Yes. Well, when I showed you the Nebraska rainwater basins and the Carolina bays, the Nebraska rainwater basins have been eroded a lot. And the reason is that it's not flat terrain. Nebraska has a lot more uneven terrain, which causes water to flow along the top. And so water flow destroys the sandy structures very easily. Whereas in the East Coast, the Atlantic coastal plain is very porous. So when the rain comes, you have all these hurricanes and storms. And in spite of all these thousands of years of storms, we still have the Carolina bays. And it's because the ground is porous, the water goes into the subsurface, and then it runs in underground aquifers. You don't have the surface flow that would erase the Carolina bays. The water just seeps down and then flows under the ground because it's very porous. And so now,
let me ask you this.
Yeah.
If you look at, we've already talked about the fact that these projectiles form an arc. And I had a great map of that I showed in one of my presentations where they're lining up along this arc feature. There are sections on that arc where there are no bays, whatsoever. Right. Do you think there may have been, and because of the 12,000 years in weathering, like the Mississippi River erased a lot of them and they were actually in a full arc?
I think, when you have an impact, it just sends material in all directions. And so one of the requirements for making a Carolina Bay is you have to have unconsolidated ground that can be liquefied. If you have solid ground, the ice just hits and shatters. And in my website, I have some experiments where I actually try to hit hard ground, and the ice, when you have small pieces of ice, the ice just bounces without making any dent or anything. But when it's wet, then you have the penetration funnels. So anything like fell in the Appalachian Mountains or in the Mississippi River basin, they just left a layer of ice, boulders and crushed ice. And I calculated maybe it could have been like 0.5 meter high from the Rocky Mountains to the east coast of the United States. The thickness of the ice chunks, just after this event, because
that's one heck of a hailstorm.
A very heavy hailstorm, yes. And so looking at this slide, I asked you, okay, suppose you were there. Where would you hide to avoid getting killed? There is no way, no place.
Not happening. All the animals, plants, people, they are gone.
Yeah. And in some places, I have calculated that there were like 8 megatons of energy per square kilometer. And so anything that was there was ground up into a pulp, made indistinguishable from the ground,
It just started hailing here. Isn't that crazy? Can you hear it?
Well, watch out for the impacts. Some hailstorms can kill farm animals. But
yeah, so what we're showing here is that it was not survivable.
Not survivable. And so this is why I have always insisted that the creation of the Carolina bays must be associated with an extinction event. And so when you take a look at the extinction events in the recent past, the 12,900 seems like the most likely. And some people have said, well, the Carolina Bays were formed along with the Australasian tektites. But see, then you say, well, in that case, some of the Nebraska rainwater basins would have deposits from the explosion of the volcanic eruptions that happened in Yellowstone, and so we don't have that. So the fact that there's also a lot of erosion in the current Carolina Bays means that they could not be very old features if they're being erased that fast. A lot of that is, of course, because of human tilling of the soil, and
So there's no way these could be hundreds of thousands of years old. There would be more erasure. There would be more areas where they're gone, and it seems like they're more pervasive now with LIDAR than ever before.
Yeah, and it would compare Nebraska with the East Coast. We can see that in the Nebraska, which has more uneven terrain and perhaps greater erosion from the northern winds and so forth, the impact structures smaller than 4 kilometers are hard to find, whereas here in the East Coast, you can see them even as small as 100 meters.
Mind blowing. All right, well, where should we go from here? To some
okay, go to start with the experiments like slide E10, adjacent impacts. Oh, hold on. Before we go that, let's discuss the black mat, okay?
Oh, yeah.
Okay, go back to the black mat picture, because
there we
go. The one before that one. See, this is the 2007 paper from Firestone et al. And it brought attention to the black mat. And he said, below, you can find the skeletons or fossils of the megafauna.
And the Clovis people.
And above that, it's just modern megafauna or modern fauna and modern people. And so a lot of people have questioned, okay, what is this black mat? And they say, oh, it's carbon rich and so forth. Well, but why is it carbon rich? And so the next slide has the paper that was published 1 year later by Vance Haynes. No, go back to the one before this one. It looks like this one. No, Vance Haynes. No, this is an experimental. Go to this one here. See, this was published the year after the Firestone had this Younger Dryas impact hypothesis. It showed the location of where the black mats occur. And one thing that I thought was very unusual was, hey, what happened to the East Coast? And so this is why I highlighted it in the next slide, showing a circle with a no, it looks exactly like that, but it has a circle on it. It looks like this, but it has a circle on it. There we go. See, I highlighted the 1,500 kilometer circle around Saginaw Bay, which is the proposed impact site. And all these black mats are outside of that circle. Why? Okay. And I thought about it. Why?
Well, because that circle was covered with meters of ice.
Not only that, it was bombarded so that all the soil was mixed up. Okay.
Oh, yeah, that too.
And then I figured that what happened is you have all this crush of ice coming down, and it's going to create powder snow, like you have in an avalanche. And so that is going to extend outside of that impact zone. and it's going to cover the vegetation with thick coating of ice that's going to flatten the vegetation and cause it to rot. And Vance Haynes found that all these black mats had fungi and showed a wet vegetation or wet signs of wet vegetation or a wet environment. And so the black mat is not caused by burning, but basically by rotting of vegetation. And so I thought, putting the circle there was could illustrate, that or why that could be. And but you have diatoms, you have fungi, and all this create the black mat.
So where do we go from here?
Okay, go to E10.
I don't know what that is. Tell me what it looks
like. That's good. See that? No, previous. Here. See, I have tried to do experiments trying to show how to reproduce the structures that we find in the Carolina Bays. And one of the ways of doing it is by saying, okay, what happens if we're talking about impacts? What happens when we have an impact right next to another one? And so this is the result. It happens that adjacent impacts transform into overlapping Carolina Bays.
Yeah, and what I find interesting is that the statement you have down here, it says the overturned flaps from the raised rims. And there was a paper that I read, I don't know if it was yours, where they did a core sample through a rim, and they actually had those types of dates where there was older. It was exactly how this experiment played out.
Inverted stratigraphy. That was in a paper by Bunch et al., which was describing some of the spherules and the impact structures. But it's interesting that in that paper, even though they found the inverted stratigraphy, they discarded that value in the middle because it was too old. They said they were still assuming some chronology. But I wrote to Ted Bunch at the time and said, hey, this goes directly with the Overton flap hypothesis required by the glacier ice impact hypothesis,
Yeah.
And so he complimented me on that. Okay, go now to the next slide where it has another conical impact cavity. No, the one before here. See, now here is a different perspective. When you make a penetration funnel, an impact cavity, you may not notice that it's elliptical until you look at it from the top. And then when you look at it from the top, then you see, hey, it's a conic section.
Is that an actual chunk of ice there in the back?
Yes, I do my experiments with ice. I make a medium of equal parts of sand and modeling clay, or not modeling clay, pottery clay, and enough water to have a soft mixture like you would have mortar for bricklayer's mortar. And then I start bombarding it with ice, to see what happens.
What do you like? Shoot it out of a straw?
No, I got a slingshot.
Oh, slingshot, yeah.
Yes. And, I have thought of ice ball cannons or something else. And I've talked to some of these people who have some of these experiments on the internet to see if they can have an ice ball cannon for having a larger kind of impact. But basically, it should scale up. In general, impacts scale from the micro impact all the way to giant impacts with many similar features. But here we see the overturned flaps, which then become the raised rims. And to go back to now, go to the next slide, which shows this one here. This is a stratigraphic restoration experiment. One of the things that bothered me a lot was they said, well, you could not be an impact because the cores don't show any jumbling or jumbled terrain. You just have a smooth terrain as if nothing had happened. Well, I think that this shows how that can happen. I had a red layer like 1 inch below the surface of this experiment. And then you can see the ice ball penetrating through that red layer. And then as you have viscous relaxation, which you accomplish by shaking, the depth of the cavity is reduced from the bottom up. And it's the layers are restored in the same sequence that they were, or in the reverse sequence in which they were parted, until at the end you end up with flat surface. And sometimes in this one you can see like a little V or something, which sometimes is interpreted as a double rim.
So why does that double rim develop? Just from the vibration?
It's like,
is it the slump down from the center and then it pushes up?
Yeah, well, that double rim is actually an incomplete closing. If we had continued the viscous relaxation, that would have closed into a flat surface. But it's just that layer is just coming together and not quite reaching the center.
So here's an excellent example of very simple observational tests to the hypothesis, and they're all corroborating the idea. Not only do we have the conical geometry correct, the ballistic angle, the preservation of the perfect ellipse, and now we have the flattening of the bays during the seismic shaking.
Right. Okay. Now, I would like to take a look at the distorted Carolina bays. Okay. And there is this one. Yes. Now, some people say, well, not all Carolina bays are elliptical. Okay. What's going on? And this one took me a while to figure out. Okay. But, when you have a hard problem, you just have to think about it a lot harder. That's all. And so what I notice here is you can see the difference in colors. The green is at a lower, excuse me, the green color is at a lower elevation. And then this purple is at a higher elevation. And so if you take a look at some of these, you notice that is the portion that is at the higher elevation that is sort of rounded up, and the bottom is elliptical. And so I said, this deserves an experiment. And so
I see what you're getting at here. So if you're on a downward slope, when you get hit, you're going to have a different shape.
Right, because you're going to have some mud flow during the viscous relaxation.
Yeah.
And so I tried an experiment like that, and that's in the next slide. There you go. See, you take a perfectly elliptical crater, and then you tilt it, and during viscous relaxation, you get the distortion. And the reason for the distortion is that you have a different angle. This is in the lower left corner of the image. The cavity creates a deeper slant or inclination than you have in the overall terrain. And so on the high side, you have faster mud flow than you do in the overall terrain. So you end up with a distorted Carolina Bay. And so that explains those particular ones. And I have looked at the uphill impacts and downhill impacts. And it's always the mud flow down toward the downslide or downslope that actually modifies the shape of the Carolina Bay.
Interesting.
Oh, this one, I want to talk about this one because this is the only experiment that has been published. And actually, it was not published. It was in a report by Raymond Kaczorowski in 1977. Okay. Now, he decided that the Carolina Bays were just made by wind and water. So he tested the idea. He started up with a circular pool, and then he put a fan blowing over it for 4 hours. But if you take a look at the little arrows toward the bottom, it says wind one way and wind the other. I think that he was not getting the results that he wanted. So he flipped the fan in the opposite direction every 15 minutes. So when they're talking about the prevailing winds and so forth, this is not what he tested. What he did is he just put the fan blowing one way and then took the fan and put it blowing the other way. And this is not something that happens in nature. I mean, you're not going to get the wind blowing from the southeast and then from the northwest, okay?
It happens here in glacial valleys, the valley I'm living in. When the sun rises, the wind blows directly one way, and then when the sun sets, it reverses. But that's in a unique steep valley near the Continental Divide.
And do you have Carolina Bays?
No.
Okay. Okay, but
moreover, even though he fudged his experiment here and did whatever he could to make it change shape, it didn't form a perfect ellipse.
That is true. That is true. It more looks like a bloated football, American football.
Yeah. Or even approaching a diamond.
There you go. But the interesting thing is that this non-peer-reviewed report has been referenced by many of the scientists proposing the wind and water hypothesis, which is the Aeolian and lacustrine hypothesis. Say, oh, Kaczorowski was right,
No, he wasn't. Look at the results.
No, he wasn't. Okay. And so basically, this concludes the experiments that have been done relating to the Carolina Bays. But now we can talk about the Y chromosome bottleneck, okay? Which I think is an effect. Go to the previous slide that shows colorful before this. There we go. See, this is the Y chromosome effective population size based on the diversity of the Y chromosome. Now, the mitochondrial DNA doesn't show this precipitous gap like that. It doesn't show that bottleneck, which means that even though the men were very constrained in birth rates, the overall human population continued to grow. And so now take a look at the next slide, which was, it's a line chart. No, the one previous to that. There. And so what this Carmen and 100 co-authors found is that at one point following the Younger Dryas, there were 17 women for one man in the birth rate. Imagine that. 17 women. So how can the population continue expanding? Well, multiple wives per man, I suppose. And so, and
interesting here, just to bring people up to speed in this line graph, you got the population from 150,000 moving towards today, and right around 70,000, which is the Toba eruption, we have a steep decline in population. And a lot of people associate this with, they call it the Toba bottleneck. And some people speculated that there was just a few thousand people left on Earth at this point.
But notice you also have that 6-to-1 ratio.
Right after that, it rises up after the catastrophe. It's
yes. And so whether it was Toba or some of the fires in the drying climate, whatever, it also created a bottleneck in the male to female ratio.
And like we were discussing earlier, you said that biologically there is some peer-reviewed information that in colder climates, male fetuses are less viable. So if after the Toba eruption, it literally got dark on Earth for a few years, it would have been very cold. And maybe they had a huge outburst of female births during that time.
Well, the report, that paper is by Catalano. And I wrote to him to find out more about his research, but I did not get a reply. But I think it's very good to know that as the weather gets colder, the males die in utero, so that there are more female births than male births.
And that means that miscarriage.
Yes. And so now I try to put this in context, and the next slide shows it in context. There we go. And you can see that this peak after the Younger Dryas is the great European civilizations, the Greek and Roman. And so it's just after the beginning of agriculture. So the beginning of agriculture, probably there were a lot of females doing the plowing or whatever, because the male population was decimated. And so here, when we were talking about the modern humans arrive in Australia, you were talking about the Toba eruption. I think it's a long projected decline in male fertility or birth rates up to about 50,000 years ago. And so whether it was a question of the weather or what ecological factors, this is something that still has to be researched. But trying to put things in
because in this time frame, the most significant geophysical events, as far as the magnetic field, occur at 42,000 years. The Lechamp magnetic excursion is the next major mass extinction. If we start at the Younger Dryas as the most recent, and you go back, the next mass extinction is at 42,000. It's not showing up at all on this graph.
No, because this only has like the human Y chromosome ratio.
But what you can see up in the 018 graph is that precipitous drop right at 42,000 years. So there is some environmental factors going on.
Oh yes, absolutely. The human race has had a hard time over its existence. Okay, and now we can switch to another topic, the Tulsa Basin. If you can get that slide. There we go. See, in my YouTube channel, I encourage people to download the visualization tool by Michael Davies, which enables you to use Google Earth with the LiDAR images. Okay. And one of my subscribers, Eric Brown, found this ellipse and he said, "Is this a Carolina Bay?" And I looked at the orientation. It points directly to the Saginaw Bay. I looked, and it's a perfect ellipse. Eric Brown works with computer-aided design, and so he has actually measured that this differs from a perfect ellipse by 0.08% or something. It's a perfect ellipse. But the unusual thing here is, if you notice, around the rim of the ellipse, there's like a berm that has been sculpted to a 15 meter berm around it. And then there's some lines inscribed in the earth. One which is horizontal, which is actually associated with the vernal and autumnal equinoxes. And then there's another line that comes to a point meeting the horizontal line, and bisecting that angle shows the summer solstice. And at 90 degrees to this inclined line, you have the winter solstice. So this was a solar observatory. And the area has been used for many things, okay? At one point, there were some troops stationed close by, and so they had the horses around there. And the ellipse itself was made into a fish pond. But there is no modern record of who carved the lines. And so one of the things that I have proposed is that this is a Native American solar observatory. But currently, we have some archaeologists from the University of Oklahoma taking a look at this. And recently, they did a seismic or a ground penetrating radar analysis, but they're going to be doing some archaeological digs. There are snakes and it's a rough terrain there. So it's hard to get into that.
It's interesting that you bring this up. I have a new channel that is just about to launch. It has almost 1,000 subscribers and no content. The channel's title is Sacred Geography, and it covers the Anasazi and their quote unquote, the Chaco roads. These are perfectly straight lines that emanate from Chaco, and they have, well, celestial importance, but more important, sacred geography. And so if a native culture out here were to find a structure that happened to line up with the summer solstice and all these alignments, by all means, they would build a berm and use it as an observatory. This is not a unique thing. What's unique is that there's not more archaeologists working this out.
Right. And the thing is, a lot of the Native American knowledge was lost because what happened in Oklahoma. They sent all the Native Americans there because it was undesirable land. So fortunately, they found oil. But
are there any other objects similar to this in this area, or is this just an outlier?
This is an outlier. I did find one more elliptical structure further north toward the border with Kansas. Okay, but this one is so well preserved that it is remarkable, and it is bigger than the Rose Bowl. The Rose Bowl is an elliptical structure, and this is slightly bigger than the Rose Bowl. So it's huge.
Like a quarter mile long.
300 meters. Yeah.
Oh, yeah, 1,000 feet.
So anyway, if anybody knows of any Native American stories about solar observatory in near Tulsa, Oklahoma, we need to hear from you. Okay, this is something that requires a little bit of context.
Yeah, it's an amazing find, and the odds of it being an accident is probably very
No,
low.
those lines don't get carved by accident. This is intentional. Not
Well,
only that,
I'm more interested in this perfect gigantic berm. We have megalithic cultures out here. We do have people building mounds all over the United States. Some of the largest earthquake works are, around this region. So I see no problem with a native culture building to reinforce this. It is a naturally occurring solar observatory that they found, and it probably had very significant importance. They say, we can't just walk away from this. This is God's work. And then they did what they did.
yes. But unfortunately, at this point, all that history is lost. And so we have to recover it.
That is unfortunate.
Okay, now let's go to the next topic, which is the sea level rise over the past 20,000 years. There we go. See, one of the things that I heard you mention was about the Pacific Northwest flooding. And the research by Harlan Bretz, who was a geologist who proposed giant flooding events and the Missoula floods. And those Missoula floods happened between, in the time range that it mentioned here, like around 14,600 years ago, in that time range. So
well, just for reference for people who are not up to speed, it was very cold. We were at maximum glaciation from about 26,000 to 18,000 years ago. Then at 14.7 or thereabouts, the temperature rapidly began to rise, and that is called the Bowling Allerod. And it was after that rise that the Younger Dryas event wreaked havoc. So sea level began rising during the Bowling Allerod. Now, the problem with, in my opinion, about talking about this graph and sea level is that at the same time, when sea level is rising, the glaciers are melting. So you're going to have isostatic rebound. So what we're looking at here is isostasy, I think, as opposed to just true sea level. What are your thoughts?
Well, no, I think that the sea level was actually rising, okay, because the Cordilleran ice sheet was melting. Take a look at the next slide, which shows the Missoula. See, this is the Lake Missoula and Lake Columbia, which are thought to be responsible for this enormous flooding events in the Pacific Northwest, which created basically devastated the land. But notice what it says up here at the very top, Cordilleran ice sheet. And if you take a look at the next slide, which shows the Cordilleran, the Pacific Northwest and the Canadian side has a northern Cordilleran volcanic province. You have the Pacific plate subducting under the North American plate, and this creates, earthquakes from Alaska to San Francisco, and you have Mount St. Helens erupting and so forth. This is due to that subduction. And so in that time frame of many thousands of years, it is quite possible that a volcanic eruption under the Cordilleran ice sheet started a subglacial melting event that could have filled up the Missoula and lakes, to cause the catastrophic event or flooding.
And that's brilliant. And the reason why I say that is because when I was in graduate school, I studied Geological, which is these are glacial floods in Iceland, and some of them are the largest floods ever recorded.
Right. This Geological are really volcanic eruptions under an ice sheet.
That's all it
And
is.
well, notice I gave you that slide a couple of weeks ago, and look at what I found today. Yesterday, a new paper was published that shows that volcanic eruption, or proof that there were volcanic eruptions under the Cordilleran ice sheet. Okay, so
Brilliant.
this is published just yesterday, and so and they have found out that some of the sediments show traces of volcanic material. And so eventually, probably it will turn out that you'll need to study the drumlins, of course, around Canada and the British Columbia. You'll need to look at the water flow and possibly find the guilty volcano.
Well, isn't this strip literally the ice-free corridor on many maps?
Well, yeah, yes. The question is, why were there two ice sheets? So maybe it was some volcanic event, or maybe it was just due to the mountain ranges or whatever. But in any case, the Cordillera ice sheet, at least in this latest paper, has been shown to have been melted by volcanic eruptions. And so it may eventually turn out that the Missoula floods were caused by a volcanic eruption and not by some extraterrestrial impact like some people have speculated.
Well, you need extraterrestrial impact for your Carolina Bays model. Now,
Absolutely.
what if it was just a rocky meteorite that hit that ice sheet, and it hit so hard that it wrung the earth? We saw Hunga Tonga, the shockwave moved around the earth several times. We're talking about an even bigger boom that could have potentially triggered catastrophic volcanism.
Yeah,
Because if
well,
you jostle the plates, you
Yeah.
may start a sequence of events that is very significant.
yeah. One thing I'm trying to be convinced that there could have been a fragmented comet that hit the Great Lakes region. And the reason for that is that when you take a look at the intersections of the Carolina Bays, where those intersections happen, a lot of them happen just to the west of Lake Michigan. Some happen to be like in Saginaw Bay, and some in other places. They don't all converge at the same point, okay? And so now that we have this method of doing the least square method for applying to the Carolina Bays, we may be able to get more exact bearings to triangulate more exactly and find out if that indicates more than one projectile impact. But there's no question that the Carolina Bays are secondary impacts. And so even though there is no crater of an extraterrestrial impact, the Carolina Bays and the Nebraska rainwater basins will eventually lead us to the location of where that extraterrestrial event happened.
Yeah, exactly. And I believe we didn't touch on the fact that a lot of the researchers that were not on board in 2007 when the Firestone paper came out have actually gotten on board in recent years. The majority of the people that were against the ice impact hypothesis are now for it. So that's a good shift. And some of the reasons are because more and more proxy data or corroborating data has come in, and it's been overwhelming. They've in fact even looked in the rims of the Carolina Bays and found these cosmogenic markers.
Right.
So when that comet came in, some of the dust coated the ice, got shot into the ground, and remained there in the rims. Is that your thought?
Well, I hesitate to say exactly how it happened. Right now I'm just struggling to show that the Carolina Bays are impact structures, and my eventual goal is to get the Carolina Bays in geology books. When you study geology, did you study the Carolina Bays in your courses?
I did. That's when I learned about them, when I got to Temple.
Right. But what was it
But
like?
I'm a stratigrapher, and so and it, you know, I was a field geologist, so surface mapping was something I learned, and
Right.
that came up in those courses because they're so unique features. But it's
Right.
like a lot of the major events in world history we don't learn about. We really
No.
truly do not get taught this. And just the fact that the Carolina Bays, and now with this LiDAR technology, is the most pervasive feature on the entire East Coast and no one knows about it. That's almost like knowing there's ice cream, but not knowing there's more than one flavor. That's crazy. Like, this is the most prominent feature on the United States.
This is why I call it the neglected Carolina Bays.
That's an understatement.
So, I think that geology has really dropped the ball here, in that everybody should know. You take a geology course, you should know, hey, Carolina Bays, they are not just like sand dunes. They are more than that. And I think even if you put them in geology books showing that there is controversy, that would be a first step. I think the next step is to say, yes, these are impact structures. And how do we know that? Because they are elliptical, and ellipses are conic sections, and therefore we know that the Carolina Bays originated as inclined conical cavities.
Very well said. Do you have any more topics? It's been a while, so let's finish up here, and we could revisit and do another podcast.
Okay, we'll see.
Yeah. It's been a pleasure, guys. Let's shout out some more. You have 2 books. They're both available on Amazon. The one is The Neglected Carolina Bays. What was the other book?
The other one is the earlier one, Solving the Mystery of the Carolina Bays.
So you can get them both on Amazon. You can check out Antonio Zamora's YouTube channel, subscribe there. He's done amazing work. And more importantly, Antonio, you had a near-death experience in the last few weeks. And I can't believe, this is a blessing that we're having this interview.
Well, I think I was the walking dead and I didn't know it.
So do you have any final words for our listeners? It's been a fantastic conversation.
No, the only 2 things. One, if you study geology and you don't see the Carolina Bays in your geology books, ask the author, put Carolina Bays in your next edition. And the other one,
Amen.
And the other one is, if you know anything about the Tulsa Solar Observatory, let somebody know about it, okay? It's very important to restore that part of our history.
Yeah, because we've lost a lot of what we used to know. And that is an understatement.
Thank you very much for having me.
It was a pleasure having you. Check out Antonio Zamora's YouTube. Go buy his books. And if you are in university and you're being taught geology and they don't have Carolina Bays in there, advocate for it. This is one of the most important topics of our times. It's related to the most recent mass extinction, which is not too far ago, and the reworking of civilizations on the planet, literally. We also have the bottleneck in the Y chromosome. There is so much happening at this time on Earth. It deserves our attention. Thank you again, Antonio.
Nice seeing you.